And it looks like we're live. So for introduction, my name is Rod McDaniels. I work for UDOT's Research and Innovation Division. We're part of UDOT's Technology and Innovation Group. I want to welcome everybody here today to the final research presentation for the project titled Image Processing and Machine Learning Techniques for Automated Detection of Planes at Utah Airports. This presentation is being recorded. Please contact me after the presentation if you would like to receive CEUs for attending the final presentation. You're invited to place questions in the chat box as the presentation is being delivered, or you can hold your questions until after the presentation and we'll have an exchange. I wanted to start out by thanking our principal investigator team at the University of Utah that's led by Dr. Abbas Rashidi. I also want to thank UDOT's Aeronautics Division for their leadership and the Research Technical Advisory Committee for their specialized research. This project's been informative. I've learned quite a few things here. A couple of new acronyms, as you might imagine. One of them is JPA, which is Joint Probability Analysis. The other one I picked up was YOLO. In this context, YOLO is you only look once. Also learned some existing tech approaches to record aircraft takeoff and landings at Utah's airports. One of those existing techs is called RCC, and that's radio click counting. This is probably an oversimplification, but that's where to determine the amount of ingress and egressing aircraft at an airport, we actually count the number of radio mic clicks and then extrapolate the usage volume from that. And today's presentation, we'll see a dramatically different approach to that. The other interesting thing I learned through this research process is that aircraft tail numbers are not standardized like vehicle license plates by any means. I also learned that the tail numbers are not always positioned on the aircraft's tail. A lot of times it's on the fuselage, and then a lot of times the font, there's great variation between the fonts. With that, I'm going to turn this over to Dr. Abbas Rashidi at the University of Utah to introduce his principal investigator team. Thank you so much, Dr. Rashidi.
Thank you, Rod, for the introduction. Good morning, ladies and gentlemen. My name is Abbas Rashidi, and I am Assistant Professor of Civil Engineering at the University of Utah. During the last 1.5 years, I have served as the PI for this project. Today, I have Dr. Nikola Markovich, Assistant Professor of Civil Engineering from the University of Utah. So he also served as the co-principal investigator for the project. And we also have Mohammed Farhadmanesh. So he's our PhD student and serve as the main technical leader, and basically he has done the main job on this project. So with that, I would like to also thank the research team and also aeronautics leadership, especially Rod and Jared, for the continuous support and coordinating the efforts for this project. So Mohammed, if you are ready, you can go ahead and share your screen with us.
Mohammed, you're muted.
Sorry, can you hear me now?
Yes.
Yes.
I had already shared my screen. I was wondering if you could see the slide. Let me do it again, actually.
Okay, good.
Okay. Is it full screen for you now?
Sure is.
Okay, thank you. Thank you, Rod and Dr. Rashidi, for the introduction. Before starting the slides, I would like, as Rod mentioned, first to thank the TAC members, Technical Advisory Committee, for their continuous support and great recommendations during the project time. Also, I would like to thank the other two groups that helped me, the airport authorities for letting me collect the necessary data, and the student team members for helping me with the data collection process. Okay, without further ado, let's get started. Today, in the final presentation, I will briefly go through the major elements of our project, starting with the importance of this work. I will review the existing methods and their shortcomings, and then discuss how I used computer vision to count and recognize the aircraft operations at non-towered airports. And I will present the details of the system performance, which is tested with several case studies at 5 general aviation airports in Utah. After that, I will discuss the implementation of the system, and the presentation will be concluded with a brief description on the future, possible future research line. Okay, why this project is important? Airport operation volume measurements are important for many reasons, namely fair allocation of national funds, quantitative preparation of airport master plans, and also for environmental studies related to pollution or noise emission. Additionally, identification of each individual operations can potentially increase the security and safety level of the airports by detecting unauthorized landings when airport is closed, or if an aircraft is involved in an incursion. Typically, airports use control towers to document their domestic operation information. And the catch-22 here is that about 97% of the United States airports are not equipped with control towers. Also, some towered airports cannot operate 24/7, and at some cases during the day or night have no active tower. That said, many attempts have been made to automatically detect and count aircraft operations using several approaches. Among those approaches, those automatic approaches, three methods stand out for their common use between the airport practitioners and the research community in this area. Acoustical counting method, ADSB based, or automatic dependent surveillance broadcast, and radio click counting. Let's see how they work and what shortcomings each one of these methods had. Let's start with the acoustical counting. Automated acoustical counters, or AAC, recognize an aircraft operation by detecting the sound of an aircraft engine associated with its takeoff. As a result, they cannot detect landing operations. They would most likely undercount the quieter aircraft operations as well. And the deployment of the AAC microphones and microprocessors requires careful consideration, as this system is vulnerable to both overcounting and undercounting. For example, an acoustical counter might confuse a taxiing aircraft with a takeoff operation at airports with closely arranged taxiway and runway. And also, it is impossible to identify the identity of an aircraft based on its sounds. ADSB, or automatic dependent surveillance broadcast, is another technology for counting operations. In this method, an aircraft is based on the aircraft spatiotemporal proximity to the runway, estimated by encoding mode S or mode C signals of the aircraft transponder, if any, which are either automatically transmitted in a periodic fashion or interrogated by secondary radar surveillance antennas. However, because of the current low equipage rate of the general aviation fleet with the required transponders, this technology cannot deliver accurate counts. Additionally, most of the current transponders do not support mode S signals and only support mode C signals, which needs interrogator to transmit this signal and do not contain aircraft XID. So basically, this technology also cannot identify most of the general aviation aircraft operations. Also, most non-towered airports are typically not inside the airspace where ADSB-enabled avionics will be required by FAA. And finally, the radio click counting method, or better to say, as Rod mentioned, general audio recording device, or GARD, which also known as radio click counter or RCC, they records pilots' radio messages while approaching the airport airdrome. It is used to estimate the airport operations counts based on the average number of radio messages transmitted on a uniform frequency during the aircraft landing or takeoff. But the number of radio transmissions depends on the pilot situation and location and may change significantly. That's why using them may lead to inaccurate estimates of the annual airport operations. And it should be noted that airports having shared uniform frequency are also prone to much more inaccurate RCC-based operation measurements. And similar to the other two methods, they cannot identify the identity of the individual aircraft operations yet. To overcome these challenges, we proposed and used a vision-based system to count and identify the aircraft operations. Vision-based systems do not require cooperation of aircraft pilots and are not relied on radar or radio. This approach is not sensitive to aircraft model like its engine sounds as long as the aircraft is visible. And computer vision actually proved effective for automating many tasks in the aviation systems. So we use computer vision to design a system conducive to different airport layouts. Two major tasks are discussed here. The possible layouts for the placement of the cameras in the airport field or airfield, and the necessary algorithms to empower the camera footage with the machine vision that eventually can detect and recognize aircraft operations. And the output of this system would be the list of the domestic aircraft operations at the associated airports. Regarding the first matter, the camera layouts, the camera deployment, during several meetings that we had, I have discussed the matter and conducted quite a few data collections with the presence of the airport managers with considerations regarding the RSA and TSA, runway safety area and taxiway safety area limitations. I have found two camera layouts suitable for detecting aircraft operations. The first camera layout is blue color coded, and the second is red color coded. The 2D view on the bottom of the slide also show how the cameras are placed on an airport diagram for each runway. Let me show you how these camera layouts would look like. This is the end camera for layout 1. In this layout, the camera layout 1, one camera is positioned at each end of the airport, orienting toward the runway and to capture both landing and departure operations. This camera layout is originally designed for having an optimum number of cameras at airports, and our data has shown that it works well since aircraft pilots run from the end of the runway to add a safety margin for a stop on the runway in case of an engine failure or rejected takeoff. In the second layout, which we have the FOV of the end entrance taxiway here, cameras are deployed adjacent and oriented toward all entrance taxiways or taxiway runway connectors. This layout helps us to have a closer range of view of the operating aircraft, which is critical to accurate aircraft identification through their tail number, printed typically on their fuselage. At the entrance taxiways, these cameras also can capture landing operations as well. These two camera layouts can work both jointly and individually, independently. In order to automatically count the operations captured with these cameras, I developed a robust computer vision framework that I want to show you. As for the computer vision part of the system, there are 4 main tasks to automate the whole process. First, we need an object detection network to detect the aircraft in video footage during the flight operation time window that we have from the cameras. And once any aircraft is detected, the computer needs to verify if the aircraft is in an operation or not, and if yes, what is the status of the flight, departure or arrival, or landing, better to say. And as for the recognition, we first extract the aircraft tail number image with a syntax detection module, and later identify the aircraft by recognizing its tail number via sequence recognition networks. Here is the simplified flowchart of the implemented algorithms in our video-based operation monitoring. As can be seen, in order to increase the accuracy of the system, a multi-frame based operation detection is implemented. The expert system first feed the video frames to the detection modules, and will start tracking aircraft only when a minimum confidence is achieved by the intelligence system. The expert system, once the aircraft exits the field of view, starts processing the extracted information to detect any information possible from the operation, and later proceeds with continuing its monitoring job. Let's take a look at the video demos for each layout to better understand the output of the system. Here are the video demos for layout 1. On the left, we can see the recorded footage from north end of the runway in Bountiful Airport, which is a Utah airport. And on the right, we have the south end of this airport. Let me play it for you. once the aircraft is detected, edge preserving algorithms are applied on the image box of the aircraft to retrieve the pixel information that are lost due to the long range of view and the blurriness effect caused by aircraft speed. And you see at the end of the operations, all information possible are extracted from the FAA database using the joint probabilistic analysis that I will explain later. The tail number region detector and optical character recognition algorithms are also triggered. And finally, at the end of each operations, a probabilistic analysis finalizes the identification and displays the aircraft information, as I said. With the conventional CPU processing, as you can see on the top part of the slide, the implemented system for layout 1 can process about 7 frames per second if only counting is needed, and about 2 to 3 frames per second if identification is also needed. Let me show you the second layout. Since we normally have a closer range of view in layout 2, in this layout, I could use more efficient algorithms for aircraft detection and decrease the computational intensity of the program. So it can process more frames per second, about 10 frames per second for the task of operation count, as you can see in the table. And also we have a closer range of view, so we have a potentially higher accuracy regarding identification of each individual aircraft. On the left, you can see the recorded footage of the end entrance taxiway at the north end of the airport, near Sky Park Airport, and on the right, the south end of the airport from the end entrance. The camera calibration and the voting-based classification, which is discussed in the report, helped us recognizing the landing operations besides the taxiing aircraft, as you can see in the footage. In this way, the number of touch and go operations will be the number of total landings minus the number of arrivals captured mostly in the middle connectors or middle entrance taxiways. And it is obvious that motion detection is not enough, since we have many other motions in our field of view in many airports. So let's take a look at the algorithms employed and implemented in this system. In this slide, I listed a few of these implemented algorithms. I use motion detection as the first trigger to reduce the system computational intensity, and deep learning based detector to increase the accuracy of the system for aircraft detections. Or YOLO, as Rod mentioned. For tracking, several correlation-based trackers are used, and for tail number detection and recognition, I also use deep learning-based detectors, since the shape of the tail numbers are typically not easy to identify. Today, I won't talk about the algorithms, but I will only explain why we needed super resolution and joint probabilistic algorithms, or JPA. And after that, I will talk about the data collection procedures. So the super resolution is implemented since in layout 1, as you watched in the video footages, landing operations cause blurry effect in the captured video frames. On the right, you can see how sharp the image looks like after implementing this algorithm. This sharpness can help with the task of tail number region detection and subsequently the number recognition task. This is done using nonlinear edge preserving and noise reducing filters for images. This filter replaces the intensity of each pixel with a weighted average of the intensity values from nearby pixels using a Gaussian distribution. And super resolution retrieve the image information. And why joint probability analysis? Let me show you an operation time window. For each operations, we have several video frames and one recognition per each frame. So the joint probabilistic solution is a method to finalize the recognition results. The first solution is a method that works based on maximum likelihood estimation. In this example, the JPA solution one would choose the right tail number, which is N287SC. But what if none of the recognitions results were the actual tail number? By recognition results, I mean after using those deep neural networks, we have these recognition results, and we have to decide which one of them are associated with this aircraft. So what if none of those recognition results are actually the tail number? I developed the JPA solution 2 or JPA 2 for these cases. So solution 1 source recognition results and remove those that the ICAO normative checks or the grammar check for tail numbers, better to say, rejects, and remove those that are not in our registration aircraft database. And if none of those recognitions are in the database, solution 2 finds the closest tail number in the registration database by using the probability distribution of each individual recognized character and calculating the maximum likelihood to give the finalized recognition results. This is done only when the first solution does not find any tail number from the aircraft registration database. Okay, enough with the technical details. Let's see how I conducted the case studies. To test the proposed computer vision system, I visited 5 airports in Utah in several different sessions. Bountiful Airport, Brigham City Airport, Spanish Fork Airport, Heber Valley Airport, and lastly, Logan Cache Airport, and collected the necessary video footage which contains different weather conditions, snowy, cloudy, and sunny, and different airport layouts with both centralized and decentralized hangars area, and different aircraft models like propellers and jet aircraft, and in different time of the day and illumination in 29 different data collection stations. Each of the 5 test locations airports had their own challenges. For example, Sky Park Airport had nearby traffic and more touch and go activities. And Logan Cache Airport, the multi-runway airport, has multiple runways. And Spanish Fork Airport had a mixed traffic of jet and propeller aircraft. Heber Valley on the right had more heavyweight jet aircraft traffic, and Brigham had more light and small aircraft operations. During the 29 data collection stations that I mentioned, 3 camera types are tested since each one of them offers different video and image configuration. In these data collection stations, I use camcorder, a camcorder, a GoPro Hero 8, and a Fujifilm X-T30 to record the footage with different video resolutions. And considering the distances imposed by runway safety area, an HD resolution with about 30 frames per second is used. Let me show you what I mean when I talk about different aircraft models. For example, we need enough frames per second in case of jet aircraft operation, since as you see, they are way faster than a single piston aircraft. During each data collection session, we check the air traffic using both radio and visual observation. Now, let's review the performance of the system, which I calculated after testing it on our collected data. In this diagram, we have the accuracies of the different software modules. The accuracies for camera layout 1 are in green, the first bars, and camera layout 2 in blue. As you can see in the first row, the camera FOV selection, both layouts almost perfectly covered the airport operations. It means that the operations were in the field of view of the cameras, with about 100% coverage for both of them. The software also was able, as you can see in the second row, was able to process the recorded videos and automatically count the number of operations with an accuracy of more than 90%. Regarding the tail number identification, using the JPA1 in layout 2, as expected, had a higher accuracy, the closer range one, with the accuracy of about 80%. And layout 2 accuracy was about 64%. As the table illustrates, based on the videos, the collected videos, only 5% error in layout 2 is associated with the software. And the remaining errors are due to the visibility of the tail numbers, like their size, and sometimes they are also cluttered or unclear. And about 6% of the collected cases did not have any imprinted tail number at all. These are some examples. For example, this aircraft did not have any imprinted tail number, or this aircraft had a cluttered tail number, which is difficult to recognize. Layout 1 is different because of the longer range of view, and the percentage of the not visible tail numbers are also more. So the above diagram shows JPA solution 2 that I discussed increases its accuracy, so does the increased video resolution. But still, as the numbers say, camera layout 2, the close range one, is a better solution for aircraft tail number recognition. In theory, there could be 2 main limitations in the presented system. Concerns regarding not OCR friendly tail numbers and nighttime operations are 2 of them. For that, a complete discussion is included in the final report regarding the list of recommendations for OCR friendly tail numbers. Typically, the easier to read by human eyes, the OCR friendlier too. So the size and font of the future imprinted tail numbers should be simplified accordingly if possible. About nighttime operations, I collected 3 nighttime sessions and only 1 operations took place in the Spanish Fork Airport runway. Actually, its runway lighting helped capturing that operation, but these operations are not significant. As it is also reported in ACRP, or Airport Cooperative Research Program Report 129, the nighttime aircraft activities in airports without lighting is much less compared to the daytime operations, which mitigates the low visibility issue if no lighting facility is existed. Okay, let me talk about the implementation. For implementation, first, a careful consideration is needed to select the best layout. Generally, each camera layout has its own advantages considering factors like the number of cameras and the accuracy of the identification. However, different airport layouts is also another factor that should be taken into account when choosing the right camera layout. For example, in Bountiful Airport, I have the airport layout here, or a Sky Park Airport. Sky Park is the second name of the Bountiful. There are large number of connectors with decentralized hangar areas. The runway and taxiway are arranged very narrowly, and the runway is also short. So camera layout 1 is recommended for this one. So is it for the Heber Valley Airport, which is similar to the Sky Park Airport. As an example, for camera layout 2, Brigham Municipal Airport and Logan Cache Airport with centralized hangars are conducive for this layout. And Spanish Fork Airport is can use both of these layouts. The camera specs, specifications, and the required video data quality and how to set the camera lenses at each location is also different in 2 layouts. Another important factor is the processing platform requirements and the software dependencies. Let me show you in the next slide. So a solar-powered camera is suggested for a sustainable recording system. Basically, we first record the videos and transfer them to the computer center for processing. As for the layout 1, a 2 to 3 times digital zoom should be set depending on the distance from the runway with a resolution of HD or higher. And since in layout 1 the recorded video targets the runway and fast-moving aircraft, at least 24 frames per second is required. However, in layout 2, even 10 frames per second would suffice, which can reduce the processing time as well. And an SD card should be used to transfer the recorded videos to the computer center. For processing the recorded videos and footages, processing computer equipped with an NVIDIA GPU is needed, and the OpenCV also should be installed on the computer, which is a free software. So let's take a look at the associated costs. Here in these tables, I listed the necessary elements to evaluate the total cost of the system. The table on the left tabulated the listed approximate prices of the required equipment for a runway, and on the right the approximate numbers regarding system maintenance. The cost of the system assembly, I mean equipment and installation together, approximately totals in the order of $8,000 for layout 1. And the remaining cost would be the maintenance cost, which differs based on the desired period for deploying the system based on the table on the right. Based on the ACRP report 129 for counting non-towered airport operations, a period of 2 weeks is suggested for each season, at least 2 weeks, for a season sample if a statistical method is employed to estimate the annual operation volume accurately. With these costs and considering the advantages of the system, it is a better solution for many airports. Aircraft counting equipment tested by ACRP report 129 included automated acoustical counters, as I mentioned in the beginning of the presentation, and sound level meters, security trail cameras, and ADSB. Each one of those has their own advantages, but also come with many disadvantages, including accuracy, cooperation problems, and feasibility, as discussed. Lastly, I would like to talk about a spin-off benefit of the project and the developed system. One spin-off benefit of the developed algorithms is that I can adjust them to also automate the aircraft tallying for the STC method or security trail cameras, which are another method for aircraft counting. In this method, security trail cameras take photos when any motion is sensed, and later the images are manually processed to see if the images contain an aircraft or something else, such as wildlife or airport service vehicles. I can adjust the algorithms to help with automation of this process as well, so it will be laborless and of course faster. In a nutshell, you give the folder containing as many as image that these cameras actually captured, and the software can count how many of them include aircraft, and if the tail number is visible, the software can also detect and read it as well. This task is usually done manually and takes a few days and even weeks, but with this software, it takes a few hours or even less. Let's take the final look at the project milestones. I'm glad that I was able to complete this project and achieve perfect results, which of course would not be possible without the UDOT support and the support of my advisors, Dr. Rashidi and Dr. Markovic. A complete literature review on the existing system is conducted, considering both a state of the practice and a state of research. Extensive data collection sessions are conducted to test the system, and the project lead conducted meticulous research to find the best settings for a vision-based operation counting system. Since it was the final presentation, I skipped many of the details in both algorithm sections and data collection sections, which are elaborately discussed in the final report. As the final word, I would like to introduce the future research line, which is edge computing by developing a standalone device for counting and recognizing aircraft operations at non-towered airports. A potential extension to this project could be prototyping the developed systems and algorithms and converting the framework into a standalone device deployable at airports. With this solution, the processing will be moved to the edge where cameras are located, which decreases the information delay with no need for transferring data costs. Development of such a standalone device requires a single board computer as the main processor and electronic engineering, software adjustments, and of course an industry mentor to conduct the pilot experience. Thank you very much for your time, and I'm ready to take your questions.
So Mohammed, could you see the chat box? We have a question from Robert Chamberlain. And I'll just read that for you. It says, can you describe again how non-aircraft are filtered in the vision detection algorithm?
Sure. Thank you, Robert, for your question. Let me bring a video footage, for example, this one. So for filtering non-aircraft operation, as you can see, there are many other possible motions in the field of view. The first trigger of the system is a motion-based detection, but there are many other possible motions. So we used a deep neural network object detector, or aircraft, better to say aircraft detector, to filter out non-aircraft operations from our field of view.
So, Mohammed, can you please use, so how does that system work? So what's the difference? For example, is it based on visual patterns of aircrafts or what?
Yeah, so here is the network. I use YOLO version 4, and the patterns that is used is actually these networks, these deep neural networks, use the appearance of the aircraft and extract the features, for example, the edges of the aircraft and any other expressive features of an aircraft to detect an aircraft compared to non-aircraft operation. Which version of the YOLO? I used YOLO version 4. And Robert, thank you, Felix, for your question. Robert Chamberlain, what are the latency requirements for aircraft detection and identification? In other words, do airports need this information immediately? Thank you, Robert, for your question. Regarding the latency requirements, it really depends on the purpose of the use of this system. For example, if you want to, if eventually we decide to use such system for using only counting operations, we could afford some latency in our data processing. But if, for example, we want to use such system for giving visual clearance, if possible, then the latency should be reduced as much as possible.
Any other questions or comments? I don't see any coming in. I do want to add that we have an exploratory meeting set up at first week of January. We've invited UDOT's data analytics team, which includes Scott and Felix, DTS, which includes Rudy, of course, our aeronautics project champions, subject group leaders, and Mohammed as well, just to have an exploratory discussion in terms of what's the potential next steps in this space. If there aren't any more questions, we can go ahead and conclude the final presentation. If anybody does have any follow-up questions, you're welcome to contact me. Looks like we might have one more comment from Robert. And that question's for you, maybe, Mohammed. In your research, was there a video feed to the computer doing the analysis, or did you take the video from the field to analyze?
I actually took the video from the field to analyze, Robert. Thank you for questions. I don't know if I answered your question.
Okay.
I appreciate it.
Hey, Rod, this is Jared. The only thing I want to add is this is a great final presentation. I appreciate you guys, Nicola, Abbas, Mohammed. This is good work done. I think, as we've gone through this process, where we started. I mean, I remember our first presentation was, holy crap, we don't know how to actually read tail numbers. To, okay, now we actually know how to read tail numbers, and not only that, we can delineate between an aircraft and a fox, which is pretty good. It seems very basic, but you should be able to tell the difference between an aircraft and fox, right? But I've seen this come a long way, and I appreciate the work that y'all put in on it.
Thank you again, Jared, for the comment and also for your continuous support to this project.
Thank you, Jared.
Absolutely.
Okay, thank you. I think that's a wrap.
There is just one more question, I guess.
Okay,
Yeah.
question from Brad.
When you are identifying the tail numbers, have you considered? Yeah, thank you, Brad, for the question. Let me show you how I consider that. For example, one of those regulations that I talked about as the normative check of the tail numbers are that you all just mentioned. That's when I filter out those recognition results using ICAO tail number normative checks. For example, if the recognition results contains a letter O or even letter I. Thank you for your question.
Okay, anyone else? Okay, I think we're all good. Thank you guys so much. I really appreciate your time investment here.
Thank you, Rod.
Thank you, Rod.
Thank you. Have a good rest of the day.
Thanks, y'all.
Thank you.